According to that? I think you said yes.
Yeah, it was. Yeah. I have to admit that I know it's right.
Yes, that was from Polish side.
Yes.
All right, I think we could start the seminar today, and it's our pleasure to give the floor to Adaricheva, who is a PhD student from Warsaw Institute of Technology, and he will give a talk on maximal sublattices of convex geometries. Please.
Thank you for the introduction. So today I'm going to talk a little bit about maximal sublattices in convex geometries, and it's a joint work with Professors Adaricheva and Silberger and Zamojska-Dzienio from my university. So let's start. So firstly, let's get familiar with Frattini subalgebras. So let's assume A is any algebra, and a Frattini subalgebra is an intersection of all maximal subalgebras of A. Maximal in the means of inclusion. So this is like the informal definition, but the formal one is by means of non-generators. So firstly, what a non-generator is. So let's take some element A of algebra A, and it will be a non-generator if for any set X, which is subset of A, such that X generates the whole carrier of the algebra, we can remove this element A from X, and we will still generate the whole carrier. So it will be the non-generator.
Yes. Algebra in a set with a bunch of functions?
Yes, with a bunch of operations.
Okay.
Yeah. Mm-hmm. Okay, so the Frattini subalgebra will be simply the set of all of the non-generators of a specific algebra. So mainly Frattini subalgebras were studied in the groups theory, and there are some simple results coming from the group theory. So a Frattini so for example, these two, if G is a finite group, it implies that Frattini subgroup of it is nilpotent. The other one is that Frattini group is always a characteristic subgroup of G. So we may also say that Frattini subgroup is always a normal subgroup as well. But I don't want to dwell on group theory. It's not the topic of the talk. I can just give a simple example that if P is a prime number, then we can consider a cyclic group of order P squared. And let's assume it's generated by an element A. So it will have a non-trivial Frattini subalgebra, subgroup, which will be generated by A taken to the pth power. So for example, for C9, these three elements will be in the Frattini subgroup. But we can transfer this idea to the theory of lattices. So lattice is an algebra with two binary operations, meet and join, or supremum and infimum. So we can also consider lattice as a poset with such a property that every set of elements has its supremum and infimum. And in the very same way as in the case of groups, the Frattini sublattice will be an intersection of all of the maximal sublattices of a particular lattice. And some remark for the sake of this talk, when we talk about lattices during this talk, we consider only finite lattices. So there is a class of lattices, which is called distributive lattices. And they are defined by two following identities. Actually, one identity of this is enough for lattices, for distributive lattices to be defined. The other one can be obtained from the first one and vice versa. And there is famous Birkhoff's representation theorem, saying that any distributive lattice may be described as a set of order filters of a particular poset, together with operations of union and intersection, which are equivalent to supremum and infimum, meet and join. Actually, join and meet in the preserving the order. Okay, so this is our first class of lattices, which we'll be considering. So let's continue. Maximal sublattices in distributive case were fully described in these two papers by Rival in 1975 and Adams, Dwinger, and Schmidt in 1996. In particular, they always have an interval as a complement, which means that if we take a maximal sublattice from some particular lattice, then what is left will be always an interval. And an interval is such a set of elements which elements are always over some one end and always below the other end. So here we have an example. This is a distributive lattice. So the elements in the circle are separate complements of maximal sublattices, which are all of the corners, this chain and this chain, which happen to be an interval. And at the same time, elements which are in the square altogether create a Frattini of this lattice, which also happens to be a chain. Okay, so let's continue. So description of Frattini sublattices in distributive case is quite complicated and was shown in the paper Abad Adams 1994. So one of the things which infer from it is that, for example, the distributive lattices as the cross product of two element chains cannot be represented as a Frattini sublattice for any distributive lattice. So shapes like this will never be a Frattini sublattice of any distributive lattice. Okay, so now we are expanding a little bit the class of lattices which we are concerned about, and we are going to bounded lattices. Now I have to say one word about this ambiguity which occurs in this particular situation, because some of you may come with the idea of bounded lattices as those which have minimal and maximal element, but this is not the case, and this is not the thing which we are using here. So the bounded lattices will have something to do with bounded homomorphisms. So let me introduce it real quick. So the idea of bounded homomorphism were introduced in the paper of Mackenzie in 1972. So let's assume that H is a homomorphism, lattice homomorphism from K to L, and H will be bounded if for every element A of L, those two sets are either empty or has the least element and the greatest element equivalently. So now we dive into the variety of lattices. In the variety of lattices, we have three lattices, which are, let's say, constructors of the whole variety by the means of homomorphism. And if we consider only bounded homomorphism, and we take the lattices which we can obtain from three lattices by the means of bounded homomorphism, we'll land in the class of bounded lattices. And the picture might be actually a little bit incorrect, because the set of free lattices in the variety has surely a common subset together with the bounded lattices. But I just wanted to show it this way, how we obtain the bounded lattices. But these are not necessarily very separate sets. They're overlapping.
Sorry, so the definition there was for the function being bounded, I thought.
Excuse me?
The definition there was a function H is bounded? It was in the previous slide.
Yeah, so the H is bounded.
And the image, okay, so
yes.
If H is bounded, then its image is considered bounded.
Yes,
okay.
yes.
Yeah.
But you have to start from the free lattice.
Free lattice.
From the free lattice in the variety. Yeah, right. Okay, so as I mentioned before, the class of bounded lattices is an extension of distributive ones. And bounded lattices generally play a big role in universal algebra, and they were studied intensively. Bounded lattices satisfy two laws, SD join and SD meet, which are generalizations of the distributive lattice identities. So these are the two laws. And there is a method to obtain a bounded lattice. It was presented in the paper of Day from 1972. And the Day's algorithm exploits the idea of doubling. So a couple of words about this algorithm. So we're starting with some distributive lattice L. We pick some interval I of it, and the double of this interval will be I crossed with a two-element chain. So, and then having it doubled, we have to somehow connect it to the untouched part of the lattice. So to do so, we have to preserve the following conditions for every A from the doubled part and for every B from the part untouched, which were not doubled. Because when we double it, we can assume that every element after doubling, so let's say we start with this lattice, we double only this element, so it has its companion. And the companion and the, let's say, original point both have to preserve those two laws. So after doubling this element, we will obtain something like this. Then we are going to double this two-element chain. So we obtain something like this. And now in the third step, we are doubling this chain. We obtain something like this. So we started from the distributive case. And what we have here is a bounded lattice. Okay, so similar facts concerning maximal sublattices of bounded lattices appear in the paper Adams, Prisnation, and Schmidt from 1997. So the first claim is that every maximal sublattice of a bounded lattice has an interval as a complement, as in the distributive case. And the other thing is that every bounded lattice is a Frattini sublattice of another bounded lattice. So this time, opposing to distributive case, we are sure that having some particular bounded lattice, we can construct some other bounded lattice, which Frattini will be exactly the first one. We don't have that property in the distributive case. Okay, so having those results in mind, in 2018, Jonathan Farley, while you were visiting Hofstra University, discussed the following problem. Is it also true for the class of semi-distributive lattices that any maximal sublattice of such a lattice has an interval as a complement? Okay, so this is an example of semi-distributive lattice, which is not bounded, and it was taken from the book of Ziezek and Mason from 1995, page 111. It is the book called Free Lattices. So the similar question was formulated by Jonathan Farley for SD lattices. SD lattices, semi-distributive lattices, do not have nice algorithmic description like it appeared in the bounded case where we had the Day's algorithm. So, and generally examples of non-bounded lattices are hard to come up with. Hence, the problem seems to be quite hard, but there is one nice result we achieved. So when a complement of a maximal sublattice of a semi-distributed lattice has an element comparable with everything else in the complement, then the complement is an interval. And the idea of proof generalizes the concept of dual pairing, which works for bounded lattices. And being specific, because I said we obtained this result, but at that moment of the project, I wasn't present, so it's really it is a result, I believe, of Kira and Silver and Jonathan, right? No, Kira and Silver. Okay, so we can even expand semi-distributive lattices, which are SD-joint lattices, and they satisfy this law above. So many partial results were also proved, assuming only one of the laws from SD-join and SD-meet. So namely, it was enough to take SD-join. And dually, same results always true for lattices where only SD-meet law were satisfied, because we have the duality between SD-meet and SD-join. Hence, we can formulate the generalization of hypothesis about SD to class of SD-meet. So the conjecture is that the complement of a maximal sublattice in SD-meet lattice has a unique minimal element and is a union of intervals with common minimal elements, which we call upper banana. SD-join, sorry. SD-join. So
I forgot. What are SD-join and SD-meet again?
So coming to this one. So this is the law which is for SD-join. And
which one is
the one here.
That's SD-join.
So lattices which also satisfy this law are in the SD-join class. SD-meet class is the dual one. So we would have to change this for meet and meet, and this one for join.
Semi-distributive sense, like both.
Yeah, somewhat. Yes. So I'll show the picture in a second, but there is a class of SD-join, SD-meet, and semi-distributive ones are those which are in the intersection of those. Yeah. But they are dual to each other. So obtaining a result in one class, we can immediately transfer a dual result to the other, to the other class. May I continue? Mm-hmm. Okay, so this is an example of SD-join lattices, and what's marked here in the yellow on the left-hand side is a complement of a maximal sublattice, which, if we see closely, it will be an interval, and it will be like this lattice 2 by 2. And here, what's circled in the yellow is also a complement of a maximal sublattice. We are excluding this point, so this is only those 5 points. So this is also this lattice 2 by 2 with a tail attached to the bottom. And as I mentioned before, the dual hypothesis lower banana about the lower banana opposing to the upper banana shall hold for SDmit. So hence, if the hypothesis would be true for SD join, then we can say that the hypothesis about SD class becomes true. So a partial result, which professors were able to obtain, is that if a complement of a maximal sublattice in SD join lattice L has a coatom of L, then it is an interval. Okay, so coatom is like the second largest element. So, for example, in the lattice. So, for example, these are coatoms of this lattice. So, if one of the coatoms is in the complement of a maximal sublattice, then we are able to infer that the whole complement is an interval. So now we are jumping to the class of convex geometries. And I promise it will be the last class we are going. So convex geometries are subclasses of SD joint class. The class has many algorithmic descriptions and representations. So that's why everybody decided to go to this particular class and check the hypothesis here. So convex geometries class is well known since the dual world times, and it was studied as a lattice with unique high redundant decompositions. And later in the paper of Edelman and Jamison in 1985, convex geometry class was introduced as a closure system with anti-exchange property. This is the anti-exchange property, which is this anti-exchange property is a generalization of convexity on the plane, and it's trying to capture the idea of convexity in the discrete world, opposing to the continuous world. So as lattices, convex geometries may be considered as those SD joins, which are also lower semi-modular. So they satisfy this law. And here, the sign of relation is considered to be direct predecessor and direct successor. So it does not mean that something is lower than the other thing. It means something more, that these are direct predecessor and successor. Okay, so duals of convex geometries are antimatroids. So this is something what combinatorics may be more similar with. And in relation to the other classes, they only share the distributive lattices with the class of bounded lattices. So this is the diagram below. So we discussed those two biggest classes, SD join and SD-meet. Their common part is semi-distributive. Here we have bounded lattices. And the common part with convex geometries and bounded ones are exactly distributed. Okay, so to generate convex geometries, we use the approach which exploits generating convex geometries by chains defined on the same finite set as it was presented in Edelman-Jamison in 1985. And this is a good point to mention that there is something what's called convex dimension of a geometry. And this is a minimal number of different chains necessary to degenerate the geometry. And here are some examples. So how the generation through ordered chains looks like. So let's assume we have two chains on the made on the four element sets. The first one is ABCD, and the other chain is CDAD. And then going from left to right, we are cutting on every we are cutting every slice and forming a sets out of it. So cutting on the very left side, we have obviously the empty set. Cutting here, we have two singletons, A and C, then A and B, B, C, and so on and so forth until we reach the cutting point here, and we have the whole sets. But after performing that, we have to be sure that this bag of items is closed under intersection. So performing an intersection, A, B, and B, C, the only element which were not present here is B. And ordering all of this by the means of inclusion, we obtain a convex geometry. And this convex geometry has a convex dimension too, because we needed indeed two chains to generate it. But there is an example where we performed the very same generation, and we obtained a convex geometry like this. But if we look closely, it would be sufficient for this convex geometry to pick only second and third chain and close this bag of items under intersection, and we would also get the same convex geometry. So it means that the convex dimension of this particular one is also a two-dimensional. Its convex dimension is also two. So the first chain is redundant. Okay. So being already in the class of convex geometries, we even went in the more narrow class, which is only those convex geometries which have convex dimension 2, and it occurred that they are dual, like only those of convex dimension 2 are dual to slim semi-modular lattices, so SPSS lattices, occurring in the paper of Chadley and Schmidt in 2012. So there's at least 56 papers studying congruence lattices of SPS, and many of these results were surveyed by Gretzer in his book published in 2023. So to obtain such a lattice, the convex geometry of convex dimension 2, we need two operations, forking and corner removals. So starting with a distributive lattice, we can do something what's called forking, which is introducing a new element in this cell and dragging the line to the very edge on each side to these two chains on the edge of the lattice. Then we can fork again, performing the same operation, but the additional thing we have to remember that crossing each line, we have to add a new element to the lattice. And there is also a corner removal, which means that we just remove the corner from the Passer diagram of the lattice. And one more corner removal. So the main result concerning convex geometries is of convex dimension 2 is as follows. Like every maximal sublattice of G is the complement of one of the forms. And now what does it mean? So J in the brackets means that we pick the smallest element, inclusion-wise, which has element j in it, the smallest subset, which has j in it. And C1 of j is the smallest subset, which has j in it, but this subset also has to lay on the first generating chain. So this is a interval created between such two elements, or we can have this complement as a sum of the disclosure of element j and the closure on a chain of element j together with such an interval, together with an interval constructed in the same manner, but on the other chain.
Good question. You said the convex dimension is a number of chains or something like that?
Yes.
How do you generate the chain, but just taking all like intersections? That's it.
Yeah. Yeah. You cut and then cut these pieces from the chains and then add the intersections.
So you're focused on one generated with two chains. So
yes. Yes. In particular, any complement is either the interval or upper banana with two maximal elements, and moreover, every interval is in the banana will be a chain. So, in order to describe the Frattini sublattices, but the time. So maybe. Okay. So we can look at this example, and in here the complements of maximal sublattices would be as follows. This part.
No, not with that. The other leg would be
this, right? So definitely this part as a row.
Actually, if the corner taken out, that doesn't. If the corner was still there, that would be.
Okay, so let's come back to that after.
Yeah.
Okay, so in order to describe the Frattini sublattice, we also need to identify which elements on the chains belong to the Frattini sublattice and which are not. So an element K on the chain Ci, so on either of the chains, is in the Frattini sublattice. Okay, so maybe let's say what is element K? So in the chain we have, for example, 1, 2, 3, 4, and 5, and element K, let's say, will be 3. So we consider it not only being 3, but everything up to 3. So it would be 1 to 3. So an element K on the chain Ci is in Frattini sublattice if and only if for K being a direct predecessor on this big chain of element T, we have a situation on the second chain that between elements K and T there is something in between. And moreover, every element of the Frattini sublattice is an intersection of the Frattini elements on the chains. So we have similar situation like when, in the case of generating convex geometry, that we pick elements from the chains which are in Frattini, and closing this bag of items by means of intersection, we obtain all of the elements of the Frattini. And there is a polynomial time algorithm to enumerate all of the maximal sublattices of a particular convex geometry of convex dimension 2, and there are at most n of them on a convex geometry with x with geometry created on n elements. And there are two claims connected with main results. So we can describe convex geometries of convex dimension 2 with a Frattini sublattice of only two elements, which is a trivial one. So let's say we know how the generating chain should look like. So the Frattini we obtain has only two elements, the minimal and maximal one. And the other claim is that some lattices cannot be a Frattini sublattice of any convex geometry of convex dimension 2. So, for example, the one generated by a cross of two chains cannot be this. And now let me give a quick argument for this, for the first claim. So, as we see in the picture, the only possible, the only operations used here in terms of forking and corner removals is either the fork of the minimal element, as in case of this and this, or a fork of a fork of such an element. So we either fork the minimal element, like 5, 7, and 9, or we fork something what was already forked from the minimal element, like in the case of 6 and 8. No corner removal was performed. And how the generating chains look like? We can divide them into intervals. So going from here, the first interval would be 1 and 2, then 5 and 6, 7 and 8, 9 and 3 and 4 as the colors appear. So the other generating chain would be 3 and 4, 9, 7, 7, 8, 5, 6, 1 and 2. And we may notice that if we look how this inner subintervals are distributed, that in the first chain, there is like I1, I2, I3, I4, and I5. But on the other hand, on the other generating chain, it's exactly the opposite order. So I start with I5, I4, I3, I2, and I1. But the elements inside the subintervals are ordered in the same manner as in the first generating chain. So if we used some other operation to generate such a convex geometry than forking the minimal element or fork of the fork of minimal element, we would change the order of elements in the generating chains in this manner that some new element would be introduced to the Frattini sublattice, despite of the minimal and the maximal one. We could also, there's one thing I also have to mention, that it may happen that we obtain the very same result as here using only corner removals. But for the sake of the presentation, we can assume that the only operations we can perform is forking and forking of a fork of a minimal element. Any other operation would change the order and introduce some new element to the Frattini sublattice. For example, corner removal would introduce a new element on the other side of the corner. And the simple argument for the second claim. So let me go to the to paint real quick. Okay. So first of all, when we have when we have two chains and we have
The board line.
pictures. So we can go through the whole exam. So let's say we have elements like this. Let's work. Okay, can I write it on the blackboard? I think it will be more
Too bad.
So let's say we have the first generating chain in non-natural order. Now we could divide the elements occurring here into three groups: the R elements, I elements, and F elements. F elements will be those which happen to be in Frattini. I elements will be those, like I'll show on some example. For example, 5 is an I element because it is followed by 6. And the same situation happens on the second chain. 5 is immediately followed by 6. So this is an I element, and this is an I element. The same thing happens with element 6 because it's followed immediately by 7. Same as here. So this is also an I. And we may notice that this order is identical in the second chain. Even 7 is following as well. Okay, so what is an R element? Element 1 here. So it is followed by 2, but on the second chain, 2 is on the left-hand side of 1. So it will be an R element. So the immediate successor of 1 in the first chain is on the reverse order on the second chain. So this is an R element. 2 is followed by 3 here. So we look what's happening here. 3 is before 2. So it is also an R element. I'll call them R1 because we're on the first chain, and an element which is R on the first chain does not necessarily have to be R on the second chain. So the same thing happens with 3. And now we go to element 4. So 4 is followed by 5. But what happens on the second chain? There is 4. It is followed by 5, but not immediately. There is a gap, and according to something in between. And according to the theorem we presented, it means that element 4 here will be a Frattini element. Okay. So the same happens with 7, because 7 is followed by 8, but here on the second chain, there's 7, some gap, and 8. So it's also F. And 8 will be R. And the final element is always F because this is this maximal. Maximal. Okay, so this is R2 because this is 4 followed by 3. But here there is 3 and 4, so the order is inversed. This will be F2. This is I and I. Here. R2. R2. F2. F2. So why am I doing all of this? This is to show that I elements preserve the order in both chains. And the one following also, the one following the I element also preserves the order here. And there is a claim, it may be argued shortly, that to find out which elements lay in Frattini and which not, we can remove all of the I elements from the chain immediately. So forget about them, because they won't change the order of R elements and F elements which are left out. And now let's look for a example proof why we cannot obtain a shape like this in Frattini. So we assume that we got 2 chains generating a convex geometry, but we have already removed all of the I elements from it. We are only left with, suppose, R elements and F elements. And now let's look at something like this. Okay, let's assume that F dot 5 is the smallest inclusion-wise Frattini element of the of this first chain. So it means that I said 1 to 5 is an element of our Frattini sublattice. And now we're gonna show that there will be some non-empty intersection with this element occurring on the second chain. So if this is an F element, all of those elements has to be R, because we assume that this is the smallest inclusion-wise on the first chain. So the only I's are removed, so the only possibility is that R's are left. So, as we remember the definition of R element, they have to appear on the second chain in order like this. But it's not necessarily that there is nothing between them. We can place also something between them. The order has to be preserved, but they can be separated by some elements as well, namely 6, 7, and 8. So now let's think where 6, where any of those elements has to appear. So we know that F is a Frattini element. So the immediate successor of 5 is 6. So 6 has to appear in at least one has to appear on the right-hand side of 5 on the second chain, but has to have something has to have at least one element in between. So the possible places for 6 is here, here, or here, or at the end. But excuse me?
Theoretically, between 5 and 4, there's something between 5.
It was like 5, 8 or something. So.
Yeah. But wherever it is, wherever it wouldn't be, we are obtaining that if it was there, we are done, because this and this become the Frattini element, and their intersection is at least 5, right? They have the non-empty intersection of element 5. But if it goes somewhere further, we can conclude that, let's assume that, I don't know, 6 is placed here. So then we can see that 4 4 here becomes a Frattini element, because there is 4 gap 6 on the second chain, on the first chain. So if this becomes Frattini, and we intersect those two, there will be at least 5 in the intersection. So there is some intersection, non-empty intersection. So in practice, it looks like we have some element, we have here, so we have to have some other element of the second generating chain that their intersection is non-empty. So shaped like this, where we have 2 elements here, and fortunately this is forbidden in the Frattini. Okay, so that would be pretty much it. So thank you for your attention.
Right, thank you. Any questions?
Looking at your picture, is it the case that the 2 generating chains